All right, a couple more examples just to sort of nail this down for you and to kind of mesh with the examples you see in the book, okay? But on the left, let's just go over a couple of the things. Right, every equation is going to look like this for exponential growth or decay. Some initial value, A, that's your starting point. And you're going to multiply that by some growth factor, B. Now, B might be bigger than 1, and in that case, you'll get growth. Or B might be less than 1, and in that case, you'll get decay. Your values will get smaller and smaller. And then X just tells you how many times are you multiplying by that growth factor. And sometimes we're talking about years, and in that case, we'll just call XT, but it's still the same thing. So now let's go over to this problem. 1, complete the table. Okay, so let's look. So we went from 6 to 2. So maybe we're subtracting by 4, but then that wouldn't work for the next one. So I could say that's dividing by 3, but I want to write that as multiplication. So I'm going to write times 1/3 because multiplying by the reciprocal is the same as division. And let's see if that keeps working. So times by a third, times by a third. Yeah, if I multiply 2 times a third, I would get 2/3. Yep, times by a third. So that's definitely the pattern. So we just got to keep doing that times 1/3. So 2/9 times 1/3 would be 2/27 times a third. And that would be 2 over 27 times 1/3 would be 2 over, what is that? 27 times 3 is 81. Okay, so that'd be 2/81. Okay, so we've completed the table. Now, does our table represent an exponential or linear function? Definitely exponential. And the reason we can see that is because we're multiplying by 1/3, right? If we're not adding each time, we're doing multiplication, so it's exponential growth. Does it represent exponential growth or decay? Well, because, and I know I just said exponential growth, I meant exponential, but because that factor we're multiplying by, so is less than 1, it's decay because B is 1/3, which is less than 1. So if we're multiplying by a number less than 1, we're going to get decay, or that number is going to get smaller and smaller and smaller, okay? And then write a rule for the function. Well, all we need is our A, our B, and our X. And so let's just look at this. Y equals, well, A is just where we're starting, and I can see that in the chart here. When X was 0, Y was 2, so A is 2. Okay, and then different color. B is just the number we're multiplying by. Well, that's right there, so it's times 1/3. And then it's just X. How many times are we multiplying by, right? And so that's our function. And graph the function. Well, I already did this on Desmo, so I'll just pop that in. So again, we're starting at 2, and then we're multiplying by 1/3, however many times. And then you can see, right, the curve that's created. You can see how we're starting at 2 and how we're getting smaller and smaller and smaller as the X values get bigger, right? Here's X is 1. Like on our chart, we did 1, there's 2, there's 3, there's 4, and you can see how it's getting smaller and smaller. And then finally, ask what is the domain of the function? Remember, domain are the X values that you can use. And in this case, you can plug in any X value you want. So just we do this like that big R, but that just means all real numbers. And we have not talked about this much, but for now, just know for the most of the equations we're going to do, you can plug in any X value you want. What we're going to focus more on here is the Y values, right? What is the range of the function? And that means what Y values might you end up with? And just notice if you look closely at the graph, as you go, you can go up as high as you want it. That's going to keep going up. But notice when you go down, we are not going below that axis. That's going to keep going. It's getting closer and closer and closer. But that's not ever going to go below the axis. We're never going to get a negative value. So in this case, you can just say y is going to be greater than 0. Okay, because you can see it on the picture. It's never going to go below that x-axis there. All right, let's do one more example. Animal population. Scientists studied the population of a species of bat in some caves in Missouri from 1983 to 2003. So from there to there, okay? In 1983, there were 141,200 bats. I already know right there, they're giving me my starting point, right? So I know my starting point is 141,200 bats. That number decreased by about 11% annually until 2003. So decreased. So I know I'm looking over here at decay, and I know my R, right? R is the decay rate. I know that that is 11%. So I'm going to look at this. I'm going to say R is 11%. But I want to write that as a decimal. So that's going to be 11 cents, which we would write like that. Okay? And then I'm just going to go ahead right now, and I know I don't want my 1 minus R, so it's be 1 minus 0.11. And that's just 89% or 89 cents. And that makes sense, right? Because you think about it, if you're going down by 11%, then after a year, you'd have 89% of whatever you started with. Think about money. If you had $1 and you lost 11 cents, you would have 89 cents at the end of that year, or 89% of what you started with. Okay, we've got that. And then finally T, and I think I went too far over to the right for the space I'd allotted, but that's okay. Now T is from 1983 to 2003, that's 20 years. So they're doing this for 20 years. So now let's just pop this in. So we already identified everything, right? The initial amount, the decay rate, the decay factor, which is right here, and then write the function. So that's all that we have left to do. So just starting at 141,200 times 0.89, and we're doing this for 20 years, and that will give you how many bats, and that is right here. You can see it on the chart, and we can definitely write that out. So 0.89 to the 20, and then multiply that by 141,200, and you end up with 13,720, roughly that many bats. Okay, after 20 years. And you can see that on the chart, right? We started all the way up here at 141,000, just over there. And each year we were going down, and we have this curve. It shows it's exponential. Each year we were decreasing by 11%. And you can see after 20 years, right there, that's what we're looking for. After 20 years, we have somewhere less than 20,000 bats left, which is exactly what we got right there.